So now let's put the convolutional neural network part aside, and let's just focus on convolution, because convolution is central to convolutional neural networks. So I first want to give you a bit of an introduction to what the convolution operation is. So let's start with a bit of some intuition. So suppose that you are recording the position of a spaceship. And this spaceship, let's assume it's a perfect spaceship, and it's taking off from Earth. So we have here the real trajectory of this spaceship that we know this is the actual trajectory it's following. And suppose that you're measuring this with a laser that might have some inherent noise involved in it. So perhaps it's due to temperature, perhaps it's due to the ambient noise, a lot of different factors that are outside of your control. So when you measure your position, in fact, you get a very noisy signal that might look like the path of the spaceship, but you know that it's not the real path due to this noise. So those of you who are familiar with signal processing, you might know there's a very simple way to smooth this noise. What we can do is use, for example, a moving average. So for every point that we've measured, we take some points before, we take some points after, we average them, and then we can smooth this signal. It turns out that this can be very easily defined using a convolution. And in fact, the way that you define how you're going to smooth the signal, you can define it in many, many different ways by using the convolution operation. So let's look at a bit of the mathematical formulation for convolutions. So again, it's an operation. Typically, it's denoted with this star operator. So here we say that S of t is the convolution of x of t with w of t. And if we're talking about a 1D signal, we can think about t here being time. In the context of convolutional neural networks, we usually refer to x as being the input, w being the kernel, and s as the output or the feature map. And we're going to come back to this. So here's how we can now define mathematically our convolution. So we have two cases. We have the case over here, which is the convolution for a continuous signal, so a signal that's smooth, and a convolution here for a discrete signal. So say, for example, a signal that we were measuring with our laser, where we're measuring at a discrete time interval. Now, you can look at these equations later on, but I want to give you a bit better understanding of these equations through animations. So let's start with an animation of a 1D convolution. So here we have our one-dimensional convolution. We have our filter, our kernel in yellow, that slides over our signal in blue and gives us our output in green. So let's look at it one more time. So we have the kernel in yellow, slides over our input in blue, and gives us our output in green. Let's take this step by step. Here was our original equation. We now have the kernel in yellow, again the input in blue, and our output or our feature map in green. And let's take a look at what's actually happening under the hood. So typically we have some numbers involved. Our input is, for example, in this 1D case, it's a vector. So we have a series of numbers. And again here we can think of our laser example. So here might be the measurements of our laser. And here we have our kernel. So we specifically designed our kernel here to be taking 1/3 of each point. So we center it on a specific point, and we take 1/3 of each point because we have 3 points, and we want to take the average. So what we do an element-wise multiplication, so 1/3 times each point, and then we sum these all up, right? This is, again, just a moving average, and you can do the calculations here. You have the math, and you can keep on doing this for the rest of your signal. And again, let's just so you keep on doing this for the rest of your signal. And now, so we have the 1D convolution. And again, this is more of an image representation just to have a good idea as to what's happening. We can now extend this into 2 dimensions. So let's take a look at a 2D convolution animation. So it's exactly the same thing. However, except of having a vector, we now have a matrix. And our kernel also, instead of being a vector, is now a matrix. And we slide over every single point, and we do the same kind of mathematical operation. So again, let's take the time to break this down. We have our input in blue, we have our kernel in yellow, and our output, or our feature map, in green. And here again is the mathematical equivalent of the operations that we're going to be looking at. So I recommend later on, when you have the time, to really take the time to look at these equations and understand what they're saying. But really, the operations that they're summarizing are what I'm showing you right now. So suppose we have our input, and again, filled with numbers. So you can imagine however large of a grid filled with these numbers. And we have our kernel. what we do is we take our kernel and we overlay it on a part of our input. So here we have our kernel. We overlay it on this region here of our input. And then we do the element-wise product for each term. So you have this one times this one times this 0, this one times this one, and you sum all of these elements together. And that gives us a single value, in this case 5, and we can place this here. Then what we do is we take our kernel and we move it one step over. And again, we do the exact same operations, and now we get our next value, which is a 7. So this is the convolution operation that we talk about when we're talking about convolutional neural networks. This is the central operation that's happening in those neural networks. So again, let's take a look at this animation. So it's just going to start over. So we have our kernel in yellow. It starts in the top left and moves over. And as you can see, we could calculate our feature map on the right. And this is the output to our convolution in this convolutional neural network. So the idea behind this is that we want the network to learn the optimal parameters of this kernel in yellow. So say we want to solve a particular task. We're not going to have one kernel. We're going to have many, many, many kernels. And we're going to let the network figure out for itself the best parameters to put in there to solve the specific task that we're trying to solve. So if it's a classification task, for example, if we're trying to figure out if a car is in an image, we're going to let the network figure out what the best numbers are to put there in order to solve this task. And again, this is going to be through backpropagation and optimization, the same theory that you saw yesterday with Gizon. So I want to take a quick pedantic timeout. So we call them convolutional neural networks. For those of you who are very astute, you might have said, well, technically that's not a convolution, because if you look at the mathematical definition, you have to flip the kernel. Those of you with a signal processing background, you are absolutely right. Technically, we are implementing the cross-correlation, but we call them convolutions. You can forget this from now on. When we say convolution, it's really the cross-correlation operation. It's kind of a detail. If you read the deep learning book, they say, this is what it is, now move on. The reason why this is the case is because the network is learning these weights. So even if we flip the kernel, the network can learn to undo this flip. Right? So it's kind of like an extra operation that we don't need. And in the deep learning community, it turns out that between cross-correlation and convolution, the word convolution was easier to say, I guess. I don't know. So you can forget this from now on. But just in case you were wondering, technically, yes, it is a cross-correlation.